Welcome to our second online lecture. This is the second lecture on chapter 27. Chapter 27 is on wave optics. And you probably noticed I went a little overboard last lecture. I think it was 2 hours instead of one. This one should be short. The point of chapter 27 is to show that light behaves as a wave. So we saw from last lecture, we had interference, between light waves. So we looked at constructive interference, destructive interference, and then we specifically looked at Young's double slit experiment that showed that when light goes through slits, it interacts with itself, something that balls can't do. If you were throwing balls, they'd go through one slit or the other. But when you shine light through slits, the light goes through both slits, and then you get constructive or destructive interference. Now, something I didn't say, scientists have done experiments where they essentially get the intensity down so low that they are sending one photon, which is a particle of light. I know the name is going to be confusing with what I'm saying now. But the light is so low intensity that they have one photon at a time. And so when you look at the pattern that it creates, you see like one here, let's change color, one here, and then one here, and then one here, and then one here. And pretty soon it builds up. So you have those peaks that are described by the diffraction pattern. So each particle of light, if you will, interferes with itself to create the distribution of the diffraction pattern. So diffraction is light bending around a corner. So Young's double slit experiment, we call it a diffraction experiment because you had light going through two slits and bending so that you had a beam that was originally coming in like this. Well, it obviously should be at the center peak where it's coming in. And then it bent around corners so that you had light that went out like that. So the point of that was showing that light has to be a wave, that everyone gave up on Newton's particle theory of light or corpuscular theory based on the results of Young's experiment. Now, today we're going to look at another optical event that can only occur if light is a wave. So we go back to, you recognize this picture. This is when we first saw anything about electromagnetic waves. Electromagnetic waves have alternating electric fields and magnetic fields, with the electric field and magnetic field tied together. So you have the electric field vector is in this case, the y direction, whereas the magnetic field vector in the z direction. They're perpendicular to each other. They have to be perpendicular. And their magnitudes are related to each other through the speed of light. And you notice here, these are exactly the same. They're both cosine of 2 pi over wavelength x minus omega t. So they're perfectly in phase. So as electric field is bigger, magnetic field is bigger. If electric field is smaller, magnetic field is smaller. Now, we're going to look at this to understand a new phenomenon, polarization. So if you have a wave on a string, you see in the first picture, the gentleman is waving the string in the x plane. And so he has a wave that's traveling the z direction with the displacement measured in the x direction. We would call this a polarized wave. And in fact, because that x is horizontal, we would say it's horizontally polarized. Horizontally polarized. Here, he's making it oscillate in a vertical direction, the y direction. So now the displacement is in the vertical direction. So this is vertically polarized. Now, from those two definitions, you can understand polarization has to do with the direction that the displacement is going. If the displacement is only going in one direction, then it's polarized. If you had him like swinging it around in a circle, if he's going around like this, the displacement would be moving between the X and Y directions. That would not be horizontally or vertically polarized. In fact, we would call that a circularly polarized, but that's not what we're talking about right now. So that's what polarization is. It has to do with the direction of the displacement of a wave. If you don't have a wave, you cannot have polarization because you don't have a displacement to talk about. Now, this third picture is actually important for us to understand what's going on with polarization. Here, he is only oscillating in one direction, but it's in a direction that has both an X component and a Y component. So he has a certain X displacement and a certain Y displacement. And so we can treat this as a combination of vertically and horizontally polarized light, or in this case, not light, or we could say it's polarized at this angle with respect to vertical. Either one would be correct because it has a horizontal component and a vertical component, or it's all in the angle of that theta. So these are examples of plane polarized waves. Remember I said circularly polarized, different things we're not going to talk about. So linearly polarized or plane polarized, same thing. So with light, our displacement was either electric field or magnetic field. And so you can talk about light polarization with either one. Traditionally, we talk about electric field, but you can talk about it with either one. It's just as accurate. So that's what I said right here. By convention, we just talk about the electric field. And if you have something that's polarized in neither the X or Y, it has a component in the X direction and a component in the Y direction. So why is this important in terms of, and what do we do with it? Well, let's learn a little bit about polarized light. If you have a random light source like a light bulb, the light bulb is unpolarized or randomly polarized. That means that if you are looking directly at the light bulb, you're going to have electric field oscillations that are oriented in all directions perpendicular to the velocity. So that's what unpolarized or randomly polarized light is going to look like, where these arrows are indicating the directions of displacement of the electric field. So that's randomly polarized. So, what produces randomly polarized light? Things that are giving off light because they're hot, like the sun or most types of light bulbs. Other things give off linearly polarized light. Examples of things that are linearly polarized are a dipole antenna, an antenna that looks like, well, let's change colors. An antenna that looks like this is going to put off, for horizontal waves, it's going to put off electric fields that are oriented like this. So that would give you a vertically polarized light. Laser beams are things we love to use with this because laser beams generally give you a, actually, I take that back. Laser beams don't give you polarized, they give you a coherent light. Okay, so that's the difference. Now, how much of unpolarized light, if I put it in front of a polarizer, and of course, if we were in class, I do these demonstrations, they're really dramatic and fun. But if I have randomly polarized light, and I put it through a polarizer, so I'm going to draw my polarizer just as a square, and that polarizer only allows vertical light through, how much gets through? Well, you look at this and you say, all of that one gets through, but none of that one gets through. And then if I take one that's on a slope like this one here, I'd have to say, well, cosine of the angle right here times the electric field gets through. And so what I would end up with is that the light that gets through is going to have to be adding up all of the possible orientations and taking cosine of the angle. And that's for the electric field. Now, to cut it to the chase, to get to the easy, what comes through is going to have to be polarized in the direction of the polarizer. So we call this the polarizer. And the amount that gets through, if I have intensity initial over here, it's going to be 1/2 intensity initial. That is, on average, 1/2 of your intensity is vertical and 1/2 is horizontal when you break it all down. So half of the unpolarized light gets through the polarizer. Now let's think about this. If you have polarized sunglasses, you have, generally speaking, unpolarized light that comes to the sunglasses, and half of that intensity gets through for unpolarized light. But what if it's polarized? We'll learn that when you have light reflecting off a surface, so here's my surface. If I have sunlight that comes like this and reflects like this, that sunlight is going to be polarized. That sunlight is going to be horizontally polarized after it was reflected. Why is it horizontally polarized? Because you had electric fields in all directions. If the electric field was oscillating in a direction that it had to penetrate that surface, then it's going to be partially transmitted at least. If it is oscillating in a direction where it doesn't have to penetrate that surface, it will be completely reflected. And so you have what we call glare, light that's reflected off of a surface. If it's a surface that is like this, like let's say the back window of the car in front of you, then it's going to be horizontally polarized. So if you wear sunglasses that only allow vertical polarization through, all of that glare is going to be blocked. And so it really cuts down on glare, making it much safer to drive with polarized sunglasses in a situation where you're getting glare off of the windows or the hood of a car. So we have a car where we get glare off of the hood. Well, if we have sunglasses that are vertically polarized, they only allow vertical electric fields through, then it will block almost all of that, and it's much safer for driving. So polarizers are things that transmit linear polarized waves in a fixed direction. You can, of course, change those. And here's a simple example of how to polarize microwaves. So microwaves are waves that have a wavelength that's longer than visible, longer than infrared, but still short in terms of if we were to measure with a ruler. So there are things on the order of a centimeter wavelength. So they're electromagnetic waves. They have electric fields and magnetic fields. If I make this little strainer, if you will, it's made out of a conducting material. So let's say it's aluminum because it looks like aluminum. Electric fields that are like this, well, we learned an electric field puts a force on a charge. So this is aluminum. It's a conductor. It has electrons that are sitting there able to move. And so if I have an electric field that's vertical on that electron, it's going to cause the electron to move in response. But when it does, it absorbs energy from the wave. And so the electric fields that are parallel to that grid vertical electric fields, because it's parallel to them, are absorbed. But if you have a horizontal electric field, because there's no place for the electrons to move horizontally fundamentally, you have virtually none of the horizontal light or microwaves absorbed. So this is a polarizer that is horizontal. It allows horizontal through and absorbs the vertical. So in our example, if we take that and we rotate it by 9 degrees, then it's going to absorb all of the microwaves we produce. And if we put it at some angle, Then the electric field. So let's think about electric field first. If the electric field has an amplitude E0, and I want to break it into perpendicular components, one parallel to the direction that is allowed through, and one perpendicular, then the part that is parallel is the adjacent side to that angle. So the parallel component is E0 cosine of theta, where theta is the angle between the incoming electromagnetic wave and the axis that is transmitted from my polarizer. So writing it out, incident wave and transmission direction of the polarizer. Well, you notice my electric field that gets through is E0 cosine theta in amplitude. But this equation has a cosine squared. Why? Because intensity is proportional to the electric field squared. So if the electric field, the intensity initial is proportional to E0 squared, the intensity transmitted is proportional to E0 cosine theta mod squared. And so if I compare those, I know those are proportionalities, but if I relate them to each other, the proportionalities cancel. And whoops, I shouldn't have done it cancel. I should have said, this is proportional to this, which makes it equal to I0 cosine squared theta, because you have the same proportionality for the E0 mod squared as you do for the E0 cosine squared. So we call this equation the law of Malus. So where do I have the law of Malus written? There's the law of Malus, or here it says Malus's law. That says the intensity that's transmitted is equal to the incident intensity times cosine squared of the angle. Now, I've already talked about this. If we have randomly polarized light, the intensity that's transmitted is 1/2 of the incident intensity. So these examples, if I have unpolarized light and I use a polarizer, the orientation isn't going to change. How much light gets through? I transmitted is equal to 1/2 I0, because we're going from unpolarized to polarized. But if I have polarized light, this one here should have been, in theory, I transmitted equals I0. And this one here, in theory, should have been I transmitted equals I0 cosine squared of 45 degrees. And this one here should have been I transmitted is equal to I0 cosine squared of 90 degrees. It's where it is on the screen. I'm too close to the edge. That's not over, it's times. So when you look at these, you can clearly see, well, that's darker. So this is not exactly right. There's a real simple reason for that. No polarizer is perfect. Nothing is perfect. And so you have some that's being blocked in addition to whatever the polarizer is blocking. This one here, cosine squared of 45 should be 1/2. So this one here should be the same darkness as that, or this, or this. And this one here, cosine 90 degrees is 0. And once again, this would have been, it's one of my favorite demonstrations. So how do we work problems with polarization? What you're going to get is problems that say you start with, you have an initial condition, and then you put polarizer or polarizers. Sometimes you'll see a word analyzer. A second polarizer is often called an analyzer. So when you see that word, don't freak out. First thing you do is the transmitted light is always linearly polarized along the transmission axis, regardless of the polarization of incident light. So if I start with light that is randomly polarized, and I write up here I0, that's what I start with. And then that goes through a polarizer that is, let's say, angled like this at 30 degrees from vertical. What's going to come out is going to be light that is oriented at that 30-degree angle, and its intensity is going to be 1/2 I0. Why 1/2? Because I went from unpolarized to polarized. Now, if I go through another polarizer, or like I said, sometimes they'll call it an analyzer. So I put another polarizer here, and I'll have this polarizer set at 60 degrees from vertical. Then the light that comes out is going to be oriented in that 60-degree direction, but the intensity, so this was intensity 1 equals, here I'll have intensity 2 equals intensity 1, because that was the intensity that came into this specific polarizer, multiplied by cosine squared of the angle between the light that came into the polarizer at 30 degrees and the polarizer orientation 60. The difference between 60 and 30 is 30. And cosine squared of 30 degrees is 3/4. Now, if I put in my I1 as 1/2 I naught, or I initial, that's how much light should be getting through that second polarizer. So as you go through the process, remember the transmitted light is always linear polarized along the transmission axis, regardless of the incident polarization. And if the incident light is unpolarized, half is blocked. If the incident light is polarized, you have to use the law of Malus, where theta is the angle between incident polarization and transmission axis. So many times people would have done this problem, they would have used 60 degrees here instead of 30 degrees, forgetting that it's the angle between this and this that they need to use. So here's a problem. Randomly polarized light of intensity I0 is incident on 2 sheet polarizers. The polarization axis of the first polarizer is vertical, and that of the second makes a 30-degree angle with the vertical. Well, this, now notice my picture says E01. We're not asked, though, for the electric field. We're asked for the intensity. And so this is exactly the situation that we just looked at. The first polarizer cuts it to 1/2 because you went from unpolarized to polarized. The second polarizer I2 is I1 cosine squared theta. Well, I1 is 1/2 I0. And theta, the angle between this and my incident light of vertical, is 30 degrees. And it brings us to the answer we just did. All right, so now a question for you, and I know you don't have clickers, it's going to be a little more difficult. What's the intensity of initially unpolarized light of intensity I0 that goes through 3 polarized, each oriented 45 degrees clockwise from the previous? So I start with a picture. Unpolarized light goes through polarizer 1, which I'm just going to make vertical. comes out. What's the orientation now? Well, it's going to be vertical. What's its magnitude? I1 equals 1/2 I0, right? That's straightforward. Now we go through a second polarizer that is oriented at 45 degrees from the first one. Sorry, 45 degrees. So what comes out has to be oriented in the same direction as this new polarizer. And the intensity of this is going to be I2 is equal to I1 cosine squared of 45 degrees. Cosine squared of 45 is 1/2. I may have screwed up here. No, it would have been way back here. Back here. No, I did 1/2. I did it right. So there's my after 2. And then I have my third polarizer, horizontal. What comes out? Should have been green. Well, it has to be oriented the same direction, so it's going to be horizontally oriented. And I have I3 is equal to I2 cosine squared of, and what's the angle here? From 45 to 90 is 45 degrees. So that's going to be 1/4 I0 was what I2 was, times cosine squared of 45 is 1/2. So my answer is 1/4 times 1/2 is 1/8. Now, you might have answered and said, why is he wasting all this time? You might have said 0 because we started with a vertical polarizer, we ended with a horizontal polarizer. Those are perpendicular to each other. So why is the answer not 0? The reason is this polarizer in the middle, it fundamentally changed the light. Initially, you had X component of electric field equaled 0. But after going through this polarizer, you had EX, that's the X component of the electric field, was not equal to 0. And so that electric field component, in fact, it was equal to E0 times cosine of 45 degrees. And so that electric field that got through in the horizontal direction, all of that came through in the final case. And actually, I shouldn't have said E0, I should have said E1, because E0 would have been out here and it had already gone through. So if I had done that, I would have had, the intensity final is going to be well, E1 mod squared is going to be proportional to intensity 1 squared. So that's proportional to, I should put proportional there. And then equal to and somewhere I messed up my math. That was 1/2. That was, well, somewhere I messed up my math. It's a little embarrassing, but it's all the way it works. I'm going to erase this just because just this bottom part. Actually, I'm pretty sure I know where I made my mistake, but it's not worth coming back. All right. Some applications of polarization. I already talked about polarized sunglasses. They are great if you are driving and there's glare. They're also great if, like, you are trying to look through water to see fish, i.e. if you're fishing, because the sunlight, once again, is going to be horizontally polarized when it reflects off of the water. And so you wear sunglasses that only allow vertical through, that block the horizontal, and you don't see the glare. You don't see the light reflected off the surface of the water, and so you can see down into the water and see fish or whatever you're looking for. But here's a very ubiquitous example as well. The liquid crystal displays like you have in your calculator or your iPhone or smartphone, they start with this. Here is supposed to be a picture of unpolarized light. And then the unpolarized light goes through a polarizer. So now it's polarized. Then we have the liquid crystal, which does a really unique thing. Depending on the voltage you put across that liquid crystal, it will rotate the polarization. So you had light that was initially horizontal oriented, and after going through that liquid crystal, if you have the right voltage, it will be vertically polarized. And then you have a second polarizer that notices perpendicular to the first. And so if you have that correct voltage, that light gets through, and hey, you see something. But if you have the wrong voltage on that liquid crystal, in this case, you have a voltage that makes it so you have no rotation, then your orientation stays horizontal. It goes to the vertical polarizer, nothing gets through, and it's dark. So I actually had a friend once who took his calculator and it had a square screen. So he popped off that top polarizer and he rotated it by 90 degrees and put it back in. Well, what that did is it reversed what was blocked and what was allowed through. So suddenly, instead of his screen generally looking light with dark numbers on it, his screen looked dark. So his screen looked like, a continuous dark screen. And then the numbers on the screen, and I don't have a pin set up for this, I'll use, that didn't turn out well at all. The numbers turned up light. So it was a cool demonstration of how that liquid crystal display works. What's cool about this then? If you wear polarized sunglasses and you look at your calculator screen and you rotate it, you can make it disappear, which is totally cool. Another example, in scattering. Scattering, we have two kinds of scattering we generally talk about, and right now we're going to talk about Rayleigh scattering. Rayleigh scattering. Rayleigh scattering is the scattering that makes the sky blue. It's the scattering, that means light hits something and comes off, from scattering centers, I'm just going to put particles, that are smaller than the wavelength. And so that means you have to have, for light, visible light is between 400 and 750 nanometers. So you have to have light, you have to have particles that are smaller than 400 nanometers in diameter to have Rayleigh scattering. That occurs if you have things like a molecule. But what happens with that molecule? How does it scatter? How does Rayleigh scattering work? You have a molecule that has charge, and if you have an electric field like this coming in, that molecule will actually oscillate parallel to the electric field, and then it can give off light in any direction that's perpendicular to that oscillation. So it can send off light in any direction that's horizontal in my example. And that light is going to have the electric field oscillating in the vertical direction. So that's basically what Rayleigh scattering is doing. But what that does then is it says, okay, you are going to have the orientation of the polarization, of the oscillation of the electric field, has to be both perpendicular to, well, that was great. Both perpendicular to the original electric field and to the direction of the new velocity. So for instance, actually I should have said it differently, perpendicular to the initial velocity and the final velocity. So in this case, the initial velocity was horizontal to the right, if it comes out like this at a 90-degree angle, then the only direction that's perpendicular to the original and the final is vertical. And so the light that comes this direction has to be vertically polarized. Now, if it goes straight, it could be still any polarization that is not going to the right. So you have partial polarization until you get to that 90 degrees where it's completely polarized. So this is really cool. And I admit, I'm a total nerd. When I wear polarized sunglasses, I love to look at the sky because I have big ball of light in the sky up here. That was supposed to be yellow. It's still supposed to be yellow. Big ball of light in the sky. And so if I look directly at that sunlight, what do I see? Well, let me first put me. Here's me. So if I look directly at the sunlight, I'm going to see the sunlight missing blue, because as the light goes through the atmosphere, blue gets scattered away because of Rayleigh scattering. Rayleigh scattering, it turns out, is proportional to wavelength to the -4, the strength of the scattering. So if you have short wavelengths, it's much stronger scattering. So blue light is scattered a lot. And what that leaves is more red light that comes through to me. So when I look at the sun is actually, I know I wrote it as yellow and I said yellow, it's actually white. But blue light is scattered away, and so I see a white minus blue, which gives me yellow color. And so actually, instead of red, I'm going to put yellow there because that's what. Okay, click the yellow, stay yellow. So that's what I see when I look directly at the sun. But let's say I look overhead in my picture. If I look overhead, then the light from the sun, which I will draw as red, it came like this, and the scattering from overhead comes like this. So I see that blue light scattered away. But because this original velocity is perpendicular to this final velocity, then it has to be polarized in the direction that's perpendicular to both of those, which is, in this case, the direction going in and out of the screen. So if I wear my polarized glasses and I look up there at the blue sky and I rotate my head, the sky, the blue sky, gets lighter and darker. When I am aligned with the polarization, that is, my transmission axis is aligned with the polarization direction, I see a bright blue sky. But when I rotate so it's perpendicular, it gets closer, well, it gets darker. Now, it doesn't get perfectly black, because the truth is, if I look in that direction, I'm going to see light that came from here and from here, and those aren't going to be completely polarized. So it's never going to be completely polarized and you're going to see black at a certain angle, but you see it get brighter and darker, and I just love that. Another thing I love to do is driving wearing polarized glasses. When you have a lot of reflection off of the roadway, I rotate my head back and forth and smile with glee as I see it get lighter and darker. Or I go to the beach and I look at the sunset and I rotate my head back and forth, and the reflections off of the water gets brighter and darker. It's all a result of this polarization. Okay, so here's pictures to better illustrate the picture I tried to draw. So you can see if you're looking directly at the sun, no change in the polarization at all. If you're looking at an angle, it's partially polarized. And if you had only this one geometry, it'd be completely polarized. All right, that is the end of this lecture. And there's already homework available to you. That homework will be due on Friday, April 3. All right, have a great day.